Hello, in this video we're going to talk about a conic section called the ellipse. Let's just start off with the definition of an ellipse. If we're just given 2 points somewhere, A and B, an ellipse is the set of points P such that the distance from P to A plus the distance from P to B is constant. So what that ends up looking like is kind of a rounded shape, kind of like you might have called something that looks like that an oval, but oval I don't think has any mathematical properties like this does. So we would call this an ellipse, and it's usually characterized by a longer axis called the major axis. What I just highlighted in green is the major axis, and a shorter axis called the minor axis. Ooh, let me do a better job there. Minor axis. So it's almost like you sat on a circle or something like that, but it is usually elongated one way. In this case, the major axis is horizontal. We'll see some examples later on in this video where the major axis is actually vertical. Let's take a look at the equation of an ellipse. Right here in purple, I have what's known as the standard form of an equation of an ellipse, and let's just take a look at the pieces we see here. I definitely see an x squared and a y squared, and that kind of reminds me of the equation of a circle, but we don't have the same coefficients this time. Notice underneath x squared is this value that I'm calling a squared, and underneath y squared is something called b squared. Another thing to note is that on the right-hand side of this equation, we have just a 1. So you might want to compare and contrast how that's different from a circle. In our picture that we have here, it turns out that this value, a squared, ends up being seen as half that horizontal axis. So that horizontal axis actually has length a, and this half, the vertical axis, actually has length b. So you can kind of see that the a squared and the b squared are telling us how long the horizontal is, and the horizontal axis is, and how long the vertical axis is. This is also centered at 0, 0. It's not a shifted ellipse. We'll see later on an example of what the equation would look like when it's shifted. Let's take an actual equation that has numerical values in place of a squared and b squared and see how we would graph it. First, I look near the x, near the y, and I notice that there's no shift. So this is centered at 0, 0. The next thing I want to look for is what's underneath the x squared term. And I see a 25. Remember, that was the place of a squared. So if a squared is 25, then a, or half the length of the horizontal axis, is 5. B is 4, because b squared is 16, and that's half the length of the vertical axis. Let's graph everything that we just said. Our center was at 0, 0, so I'm just going to put a mark there to know that that's the center of the ellipse. I know that a was 5, so I'm going to count out 5 units to the right and 5 units to the left. I just created the horizontal axis of our ellipse, and I knew it was the horizontal one because the 25 showed up underneath the x squared. And when I think x direction, I think horizontal. When I think y direction, I think vertical. So I'm going to go up 4 and down 4. And then I do the best I can to connect those points. I think I can do a little bit better than that, though, to make it look elliptical. That's not great, but that's the best I can do on this screen. So notice it's not a circle. We have a horizontal major axis. The total length of the major axis is 10, right? And then the length of the minor axis, in this case it's the vertical axis, half that length was 4, the total length is 8. The endpoints of the major axes are called vertices. So whichever axis is longer is known as the major axis. The endpoints of that axis are called vertices. The other points, or the points that the endpoints of the minor axis, those are called co-vertices. So we have a vertex, a co-vertex, and then another of each. So it just depends which axis is longer. That'll tell us whichever one is the major axis. And then from there we can see which are the vertices and which are the co-vertices. Let's do another graphing example. Notice we can actually see a shift this time. Going by what we know from circles, I can actually see the center of this ellipse. It's shifted 2 units to the right and 1 unit down, so our center must be 2, -1. It follows that same structure as we saw in the equations for circles. A here, I look under the x to see our horizontal movement. I see that a squared is 9, so a is 3. B squared is 36, so b is 6. Let's plot the center, 2, -1, and that's not on the ellipse. It's not a point on the ellipse, so I make a little X just to remind myself it's not actually part of the graph, but it's helping us get the picture. A is 3, so I'm going to go 3 units to the right and to the left, because that's our horizontal movement. And B is 6, so I'm going to go 6 up and 6 down from the center. And I connect that as best I can to make an ellipse. Notice this time the major axis is vertical. So our vertices are actually here and here in red, and our co-vertices are actually here and here in black. So I would say that this time, because our major axis was vertical, you can see that how that looks a little bit different. It's just, instead of elongated horizontally, it's now just kind of stretched vertically, but that's perfectly fine. There's our ellipse. Let's just do one more example here. Let's try to go backwards. Here we're given a picture of an ellipse, and I'd like to try to write the equation of our ellipse. So first I'm going to notice that the major axis is vertical, so that tells us that our b value is probably going to be bigger. Notice where the center is. The center is right here, and I can count from the center to a vertex as 1, 2, 3, 4, 5 units. Oh, let's say that. It's 5 units. So I know that that's the vertical distance, so I know that b is equal to 5. B squared was what I was always writing, is what showed up underneath the y squared term. The other thing I want to notice is our distance from the center to a co-vertex is 2. So I know that A is going to be 2. The other piece of information that's super important is where the center is. That's going to tell us the shift. That is at the point -5, 5. Looks like that's where that center is. Let's see if we can fit everything into the equation. I know that we need an x plus 5 squared to show that that ellipse had a left-hand shift, over a squared. So if a was 2, a squared is 4. I know that in an ellipse we're adding the 2 terms, and I know that we shifted 5 units up, so it's going to be a y minus 5 squared in the equation, over b squared, which in this case is 25, equals 1. We've seen that all of our ellipse equations, the 1 is on the right-hand side. So we'll see that it's actually, they're very much related to circles. A circle is actually a special type of ellipse. Of course, we know where we can see the center, and then A and B are just the same in a circle. But this form is nice to have an ellipse. It's nice, when we're graphing an ellipse, it's nice to have it in a form that looks like this, so we can easily see you know, our center, our A value, our B value, and graph it pretty easily. So that 1 is always showing up on the right-hand side. Other things we might have to do with an ellipse is maybe you won't be given the ellipse equation in such a nice form. We might have to complete the square to find the center in our A and B values, other things like that. But this is the basics. If you can get your equation in this form, you can find your center, your A value, your B value, you can plot it, no big deal. Have fun!